And we are in a moment going to listen to a video on JSONiq, which has nothing to do with XML. So that's always great for for people that want to know that declarative is not part of XML, although many of the people here are part of the XML community at large.
Hello and welcome to our presentation on adding JSONiq update semantics to the RumbleDB query execution engine. I'm David Loughlin, and I'll be presenting this work that was conducted at the ETH Systems Group with Ghislain Fourny. Now, looking at JSON, hopefully we're all somewhat familiar with JSON data. I think of it as a tidier XML, both following the document logical data model, representing nested hierarchical data with as much heterogeneity in the types as you require, and giving this lovely tree model to visualize the data. But on top of this, JSON offers a much more human readability while maintaining the ability to represent heterogeneity, making it the perfect use case in big data, tackling the variety and contributing to the variety in big data, making it useful for software engineering development environments and web API exchanges. And it achieves this heterogeneity through its structured and atomic types, like the object seen in the top rectangle with its key value pairs, and the arrays seen in the second red rectangle. Now, this typing creates a mismatch with the normal rigid structure of the relational model that many processing systems are used to, making it difficult to analyze with RDBMSs like PostgreSQL without additional features and non-native storage formats. To illustrate the difficulty of analyzing JSON with SQL, consider this query. Here we see a query processing over an array and nesting data from another sequence of objects. And then we have the opposite. We see unnesting of data from the foobar. While each of these queries enable document processing, they force the document model to conform to the relational model, making for unintuitive and inexpressive querying. So let's look at a more native format. JSONiq aims to tackle this lack of expressivity by maintaining the familiar and query-aiding aspects of SQL, like being set-oriented and declarative, everything people are familiar with, while also natively introducing the nested heterogeneous aspect of document data, where input and output sets can be seen as flat sequences of items, but each item can have its own nestedness. However, this semi-structured model often means that, as currently implemented in many systems, the data cannot be effectively modified in place. In fact, frequently updating an item in JSON means completely overwriting the item even when only one value in the item is changed. To remedy this, JSONiq introduces updates, using a lot of inspiration from the xQuery update facility, if anyone's familiar, through a structure called pending update lists, or PULs for short. These PULs are simply an unordered collection of update primitives, we'll get to that, all generated within the same snapshot and adds to be applied at the same time. The update primitives, on the other hand, just describe the changes of state that are to be applied to an item, be the changes, insertions, deletions, key renamings, or replacements, what have you. For JSONiq, this introduces some additional expressions to each of the possible kinds of states that change and transform expressions that allow copies of items to be updated and maintain immutability in the language. Crucially, the updates within a PUL are not yet applied, meaning generated PULs do not yet make the changes visible when processing. But how are these PULs generated in the first place? Well, in standard JSONiq, each query expression generates a sequence of items. But with the introduction of updates, JSONiq expressions can now also describe updates to be made and so also return a PUL. Crucially, only the resulting sequence or PUL can be populated, and not both, so as to avoid discrepancies in output sequences containing items that may be populated. Thus, JSONiq classifies these expressions for systems. We have simple expressions that don't do any updating, cannot produce a PUL. We have basic updating expressions. These constitute the new expressions that describe update primitives. We have updating expressions that are either basic updating expressions or nested updating expressions. Then we have vacuous expressions to catch edge cases. Now, given all the new methods for updating JSON data, there arises the potential for duplicated or conflicting updates, and updates that can be applied together without conflict. Thus, PULs can be merged together to form another PUL, following some intuitive rules regarding the possible update primitives. For example, when you're inserting into the same object, two update primitives may be inserting different keys and so should be combined to form a single update primitive containing all the new keys. However, if two object insertions are to have different values for the same key, that results in a conflict and thus an error downstream. Similarly, for object deletion, you can combine the keys to delete, and if the same key appears in multiple update primitives, then that's fine, we just remove the duplicate. And finally, just like with object insertions, object replacement, as long as there's no conflicting keys, then there isn't any conflict. Similarly, we have these merging semantics for arrays, as one would expect, but instead of with keys, it's with indices. Finally, and perhaps most crucially, PULs will eventually apply their updates to the specified items. And in doing so, they find the item in the sequence and do as the update says. Insert into the object, delete at this index in the array, what have you. Now, since these updates are all to be applied in the same snapshot, the order in which the expressions described the updates should not matter. Rather, updates that will conflict already have been identified in merges, and so all the updates to be applied should be applied. Finally, once the PUL has been applied, all update primitives have been removed and the snapshot is ended. With this new specification for JSONiq updates, it begs the question of how to implement them in a JSONiq execution engine, and our presentation today will explore our solution for this in RumbleDB. For those who don't know, RumbleDB is a JSONiq query execution engine, enabling query processing on heterogeneous datasets from the small to the big. It has a simple but effective processing pipeline to go from the query to the resulting sequence. And it is in this pipeline that we will be targeting our solution. Now, before we can dive into the technical details, we must first address the critical component of updates not described by JSONiq updates, and that is the matter of persisting these updates to storage. After all, what are updates without persistence? Thus, we will be looking towards the Delta Lake format provided by Databricks that offer an abstraction that aim to achieve ACID compliant storage using write-ahead logs for a set of Parquet files to represent data sets. With this, we can aim to achieve ACID compliant updates for the update primitives available in JSONiq, thus allowing for the heterogeneous expressivity for the JSON data model and updates without sacrificing aspects of either. The final goal from here is to introduce JSONiq updates that can be persisted into RumbleDB. And to do that, we will be altering the query processing pipeline to produce sequences and PULs as described. The first and simplest step is introducing the syntax for updates outlined in the JSONiq specification. This is easy to accomplish with the Antler4 parser generator, and it's just a case of plugging in the necessary syntax for each of the new expressions. With the abstract syntax tree ready, the tree can be translated into an expression tree, and standard visitor patterns can add the expression classification information. Similarly, once we have the expression tree, we can translate this into an iterator tree. To do this, we add iterators for each of the new updating expression types and propagate whether a non-empty PUL can be produced via some simple is and getter methods. Here, the isUpdating method reflects the classification of the expressions being basic updating or updating regarded as true. However, before any update can be processed, we must address when an item can be updated. Much like JSON data, JSONiq queries allow for nesting to access the arbitrarily nested values. The transform expressions introduced earlier can also nest to allow updating both a value nested within an item and the item itself. However, to maintain consistency across levels of nestedness, JSONiq asserts that the items being copied, those marked for updates, in transform expressions, can only be updated at the level of the transform expression and no deeper, or no higher. Thus, we add metadata to the items that states their mutability level to indicate whether an item can be updated or not. Further, tracking immutability is as simple as checking if the mutability level is -1. This results in highlighting exactly the level of nestedness that an item can be updated at, allowing iterators to perform a simple check at runtime. Now, here we get to the fun part. How we represent update primitives and PULs respectively, such that they can be produced by iterators. For update primitives, we start by considering how we can create an interface that they can all conform to for easier processing later. Some update primitives, like insert into object at the top, can only update an object item using data represented as another object item. Hey, insert these keys from this object into this object. While others, like insert into array just below, only update array items at a specific integer index, and they can insert many items at this index, giving the item star you see on the screen. In this way, each update primitive has a target item that is to be updated, i.e. the original object item for the insert into object and the original array item for insert into array. And they might have a selector item that identifies where in the target to update. And they may have a content item with data to update the target with. With this decomposition, we can form an abstract interface for update primitives as some 3-tuple with possible missing values for the selector or the content. Here, for insert into object and insert into array, they can be respectively defined as a target content tuple with no selector and a target selector content tuple. Now we can apply this decomposition to each update primitive, giving something like this that we can use to abstractly understand what each update primitive's structure is like. Now we must put these update primitives into a PUL and add the functionality for merging and applying them. Due to the potential for merging and applying large numbers of update primitives, the choice of data structure for PULs is critical. An array is simple to implement, but discerning between update primitives and finding compatible merges requires a lot of lookups and a lot of conditional checks for compatibility. Thus, we can utilize the decomposition to embed this lookup for compatibility into the PUL data structure using a set of ordered maps. Update primitives that can conflict and/or be merged are placed into the same map that indexes elements by their target, selector, and content where possible. The object insertion map is simple, mapping targets to contents, while deletions and replacements share a single map on an object, differentiating from one another by whether the content is null or not. And we have similar maps for the array update primitives. With these maps, insertions into a PUL automatically merge individual update primitives. For example, inserting a delete from array update primitive would result in the PUL inputting the decomposed primitive into the delete replace array map, looking up the array target, the same array index, and noting that the content is already there and null, meaning no delete has to be inserted, effectively merging. Further, merging two PULs together is as simple as iterating over one PUL and inserting all the update primitives into another. Now, the next challenge is that of applying the update primitives within a PUL. While the order of updating expressions does not matter in the query, when applying updates to an array, certain updates, namely insertions and deletions, will change the indexes of values in the array. For example, inserting at an index and then deleting at an index after the insert will result in a different array depending on whether you insert first or delete first, as seen on the board. From this, we notice that a deletion at a given index x will decrement the indexes of all values after x, while an insertion at the same index x increments the indexes of all values following x and the value that previously was at x. Thus, for a deletion and insertion at a given index, the deletion will not alter the index of the insertion, but the insertion can change the index of the deletion. So for insertions at a given index, we have to perform them last. Using the same principle, updates at lower indexes change the index of updates at later indexes. So array updates must be performed in descending selector order, where these selectors are the indices of the targets. To finally apply the updates, then, we rebuild the update primitives from their decomposed form in the PUL maps. And by iterating over these ordered maps, ordered by these selectors, as described, we can ensure that the order of application is then correct. This then leaves us with the task of persisting updates. As much of RumbleDB already uses Spark and data frames to process data, allowing for the processing of delta tables is as simple as creating an iterator that can open delta files and expose the data frames. But due to data frames using a more relational model, identifying the target of an update requires a new approach. Items to be updated in a delta table may be nested within objects or arrays, as seen here with the foo column and the row in the red box, meaning a simple row ID and a column is insufficient to identify an item. We can't know that we're talking about this row string just from an ID2 and the foo column. Rather, an item is identifiable first by the path to the table in which it resides, i.e. the table location, then the row ID, And finally, the path in to the nested object denoted by a string containing dots to access values at specific keys in an object, and square brackets for indexes in an array. Notably, the first key in this path in string will denote the column. Deciding whether an update is to then be applied to an item or a specific value in a delta table can be found with just some simple logic based on the newly added item identification. Here, the update primitive can find the proper application method, where if the table location is null, then the item is fine to be applied as normal. There is no delta table involved. Otherwise, we're going to look into delta table processing. If it uses an array in the path, then we're going to have some specific methods to update the array. And if there is no array, then we can just wonder if it updates the schema, creating again two different branches for the methods required. While the goal of this work is to introduce the expressivity of JSONiq expressions for nested heterogeneous data, to updating such data, we will now look at some performance analysis to gain insight into some future work. To effectively analyze these updates and find differences in how they handle document and relational data, we're going to look towards the TPC-C dataset for homogeneous relational data and the GitHub archive for document data, both of which we're going to store in delta tables. For each benchmark, we will be comparing RumbleDB with the JSONiq updates to implementing the same updates in Spark SQL. All of this having been performed on a fairly simple machine with about 16 gigabytes of memory and nothing special. Now, for the TPC-C data, we see that Spark SQL maintains a 1 second mean execution time across all tuple counts, while RumbleDB's execution time scales linearly with the tuple count due to Spark SQL being able to batch and parallelize the updates, while RumbleDB is applying an update per tuple. We see a similar story when analyzing the GitHub archive benchmark, as the green line performing nested insertions and the red line, which does not, have similar performance, but the green line has a slightly higher execution time as it alters the schema, while the red query does not. Nevertheless, the difference diminishes with more tuples. The blue line, however, sees the highest execution time by far, and this is because it is updating data within nested delta table arrays, and these arrays require full materialization before any change can be made due to limitations in the delta table API. So with all of these insights, we can draw some conclusions. This work has managed to bring JSONiq updates to RumbleDB, laying the foundation for future work on expressive updates for heterogeneous data. These future updates could also benefit from the Target-Selector-Content decomposition of update primitives that we proposed and the mutability scoping to manage nested updates in queries. And we confirm the efficacy of these abstractions through our ability to fairly quickly integrate the persisting of updates to delta tables. However, the results against Spark SQL indicate that there is much room for improvement with respect to performance, leading on to some potential future work. There's much room for improvement with the update primitives, as they can batch similar updates together such that the updates can be applied to a whole collection of items using RDDs or data frames, allowing for some batch processing and parallelization, bringing the number of updates per tuple down and allowing for closer performance with Spark SQL. And we can ensure that update primitives only target non-structured items, i.e. the atomic items, to avoid materializing large arrays for which only a portion of them have to be updated. And while our work has focused on persisting updates using delta tables, it's also an interesting endeavor to make big data tools more available to one another which can be accomplished for RumbleDB by persisting to a document store like MongoDB, and in doing so, potentially exploits the processing benefits of using a native document storage system. With that concludes this presentation. The work presented is available in the RumbleDB version 1.22, Pyrenean Oak, and I look forward to your questions. Thank you.